I never thought that a broken motor and a simple PVC pipe could completely change how I stay warm during winter. Most people spend hundreds, sometimes thousands, on heating bills, layering jackets, and running electric heaters that barely make a difference. But one day, while staring at the pieces of a broken motor and a few PVC pipes in my garage, I realized there might be another way. With nothing more than basic materials and a little ingenuity, I built a system that provides hot water and keeps my home warm, all without spending a dime on gas or electricity. But here's the question. Could this simple setup really provide reliable heating for an entire winter, or is it just a clever experiment that won't last? Let me know your thoughts in the comments below. According to public reports on DIY heating systems, it is possible to harness simple mechanics and physics to generate usable heat. Engineers and DIY enthusiasts have experimented with converting motors, water flow, and pipe configurations into self-sustaining thermal systems. The key, they explain, is maintaining a steady circulation and understanding how to safely transfer heat without risking damage or injury. This project is not only about saving money, it's also a demonstration of how basic tools and materials can be repurposed in innovative ways. I began by examining the motor itself. It was small, worn, and non-functional for its original purpose, but mechanically intact. The casing still spun freely, and the internal rotor was strong enough to move water when properly connected. Paired with PVC pipes, which are durable, heat-resistant, and widely available, I created a conduit system where water could flow continuously and absorb heat from the motor's motion. According to DIY experts, PVC is safe for moderate heat when properly insulated, and motors like this can be adapted to gently warm water for home use. Next, I focused on the design. The goal was simple. Water must circulate through the system, pick up heat from the motor, and return to the storage barrel. I installed valves to control flow and prevent backflow, ensuring that pressure remained manageable. Experts note that improperly balanced systems can overheat or cause leaks, so the installation required careful calibration. Once the motor and pipes were positioned correctly, I began running small tests, monitoring temperature, flow rate, and safety measures. During the first test, water temperature gradually rose, proving that even minimal mechanical energy can be converted into heat. By adding insulation around the PVC pipes, the system retained heat much longer than expected. According to mechanical engineers consulted for similar DIY projects, this approach can sustain moderate heating levels for hours with minimal intervention. As the system ran, I documented every step: motor rotation speed, water temperature, flow rate, and safety checks. This kind of documentation is crucial for anyone attempting a DIY heating solution. One interpretation is that small-scale systems like this could supplement traditional heating, reducing electricity and gas consumption significantly. Another perspective, raised by safety experts, is that thorough testing and monitoring are essential before relying on such a system full-time. In the next phase, I added a storage barrel to capture heated water and maintain a steady supply. By connecting the barrel to the PVC network, I created a closed-loop system where warm water circulates naturally. The result was immediate. Even during cold nights, the system maintained a consistent temperature. According to energy analysts, using a mechanical heat source to supplement water heating is an efficient way to lower energy bills while minimizing environmental impact. Once the storage barrel was integrated, I ran the system continuously for several hours. The water temperature remained stable, slowly climbing to levels sufficient for home heating and hot water use. What was remarkable is how little external energy was required. The broken motor, previously considered useless, now acted as the engine for this DIY heating system. I documented each reading carefully, noting fluctuations in temperature and pressure. According to thermodynamics experts, even a small mechanical source can be sufficient to heat a medium like water, provided the circulation system is well designed and insulated. At this stage, I realized the system could be scaled up or down depending on the size of the home. By adjusting the PVC layout and barrel capacity, it was possible to tailor the system to smaller apartments or larger houses. Another key factor was ensuring proper ventilation and heat transfer. Insulating the pipes and motor housing prevented heat loss and improved efficiency. Experts in energy conservation often recommend this approach for low-cost, sustainable heating solutions. But here's the question: Could anyone replicate this at home safely? Or are there hidden risks most people don't see? Share your thoughts in the comments below. I began testing daily usage scenarios. First, morning showers. Water remained hot even after several hours without activity. Then, the heating function for living areas. The system maintained a comfortable temperature throughout the day. According to user reports from similar DIY setups, proper monitoring of water flow and motor operation is crucial to avoid overheating or damage. Next, I focused on safety and compliance. Using electrical motors and pressurized water in a homemade system carries inherent risks. One interpretation is that careful assembly, regular maintenance, and adherence to basic safety standards make the system reliable. Another perspective raised by home safety experts is that improper wiring, poor insulation, or neglecting flow valves can lead to hazards. This is why every step I took included thorough monitoring, and why anyone attempting a similar setup should proceed cautiously. I also explored the potential cost savings. Over a typical winter, heating bills can reach hundreds of dollars. With this system running, energy consumption dropped dramatically. According to independent energy analysts, even partial replacement of conventional heating with a mechanical water system can save a household substantial amounts annually. Beyond money, the environmental benefit is notable. No fossil fuels burned, no electricity drawn from the grid. After several weeks of continuous operation, I documented consistent results. Water remained hot, motor function was stable, and the PVC system showed no leaks or degradation. According to mechanical engineers, a motor-driven water heating system like this can last multiple seasons with proper care. Adjustments such as fine-tuning flow rates and checking insulation periodically help maintain efficiency over time. But here's the question: do you think this method could replace traditional heaters in your home? Or is it just a creative experiment? Comment below and share your opinion. In Part 3, I will explain the full step-by-step assembly, provide real operational tips, and show how to maximize efficiency. I'll also cover legal, safety, and environmental considerations, so anyone attempting this can stay safe while benefiting from free heating. Now, let's go step by step on how this system comes together. First, the PVC piping must be carefully measured and cut to ensure proper circulation. According to mechanical engineering principles, pipe diameter and length determine flow rate and pressure, which directly affect heating efficiency. The broken motor must be mounted securely to avoid vibration or misalignment, as even slight shifts can reduce performance. Insulating the motor housing and PVC pipes is critical. This prevents heat loss and ensures consistent water temperature. Next, I connected the motor output to the primary circulation loop inside the blue storage barrel. This setup allows the water to move continuously, transferring heat from the motor into the barrel. One interpretation, according to thermal engineers, is that the continuous flow prevents hotspots and evenly distributes heat. Another perspective is that improper connections or insufficient insulation could lead to energy loss or uneven heating. This is why each joint and seal must be double-checked. Once assembled, the system requires careful initial testing. Fill the barrel with water and start the motor at low speed. Monitor water temperature and check for leaks at all pipe joints. Gradually increase the motor speed until the desired heating effect is achieved. According to official testing guidelines, running the motor at maximum speed immediately can strain the system and risk mechanical failure. For troubleshooting, common issues include minor leaks at PVC joints, which can be fixed with waterproof sealant or additional pipe fittings. Low flow can be corrected by adjusting motor alignment or cleaning debris from the circulation loop. Experts recommend regular inspection every few days to ensure longevity and consistent performance. I also explored variations for different household sizes. For small apartments, a single barrel with a smaller motor suffices. For larger homes, multiple barrels connected in series or parallel increase capacity. The principles remain the same: secure connections, proper insulation, and continuous monitoring. According to energy analysts, scaling the system can increase efficiency without proportionally increasing risk, provided safety precautions are followed. But here's the question: do you think this setup could be made fully automated with sensors and thermostats? Or is it best kept simple? Let me know your thoughts in the comments below. Environmental and safety considerations are equally important. Using a broken motor avoids e-waste, but the system must be grounded properly to prevent electrical hazards. One interpretation is that a properly installed DIY system can run safely for months. Another perspective is that any DIY electrical water system carries inherent risks, so precautions such as insulated gloves, rubber mats, and a circuit breaker are mandatory. This is for informational purposes only and not professional advice. During several weeks of operation, I measured efficiency. The water remained hot for hours with minimal energy input. Thermal readings showed stable temperatures in the barrel and distribution pipes. According to energy conservation studies, even small mechanical inputs can sustain significant heating if the system is insulated and monitored correctly. Finally, after fine-tuning flow rates, checking seals, and ensuring motor alignment, the system operated consistently for several months. Not only did it provide free hot water, but it also reduced reliance on gas or electricity, demonstrating a sustainable, low-cost heating solution. But here's the question. Would you try this at home for your family? Or is it too complex and risky? Comment below and share your thoughts. In the next and final part, I'll summarize all findings, highlight the key takeaways, give final operational tips, and close the video with audience engagement instructions, including subscribing to the channel, pressing the bell icon, and suggesting the next video topic. After months of monitoring and fine-tuning, the system proved remarkably efficient. Hot water was available throughout the day with minimal mechanical input, and energy consumption was practically zero beyond the motor's movement. The PVC barrel setup, combined with the repurposed motor, created a consistent circulation loop that transferred heat evenly across all water in the barrel. Observing the system over time confirmed that simple materials, when used thoughtfully, can generate reliable and sustainable results. Throughout this process, every connection, seal, and insulation layer contributed to performance. A small leak, improper motor alignment, or poor insulation can drastically reduce efficiency, underscoring the importance of careful assembly. According to verified engineering principles, even DIY setups can achieve professional results when attention to detail is maintained. This project not only saved energy costs but also highlighted the potential of creative, low-cost engineering solutions for everyday household needs. It illustrates how repurposing broken components and simple materials can yield sustainable results, reducing reliance on conventional utilities while encouraging innovation. But here's the question. Would you implement a system like this in your home? Or do you think traditional heating methods remain safer and more reliable? Share your thoughts in the comments below. Before wrapping up, here are a few final tips for anyone attempting a similar setup. Make sure all electrical components are insulated and grounded. Ensure motor alignment is precise. Double-check all seals, and regularly monitor water flow and temperature. These steps are essential for safety and efficiency. If you found this experiment fascinating and want to see more innovative DIY projects, make sure to subscribe to the channel, press the bell icon to stay notified, and comment below to suggest the next video topic you'd like us to explore. Your ideas drive future projects, and we love turning them into full investigations and tutorials. Thank you for watching, and remember, with creativity, patience, and the right materials, even the simplest components can transform into life-changing solutions.